Okay, perfect. So first of all, let me start the presentation. All right, you can see the presentation properly. Yes. Okay, so let's get started. So this is your short guide to logistic regression. Okay. Um, in this presentation here today, I'd like to give a detailed walkthrough of how logistic regression works and how to implement it from scratch. Let's get started. So here's the agenda for today. So I'm going to talk about who I am and a quick poll, and then I'm going to quickly cover what you will learn from this session. And then I'm going to talk about these important different concepts, related to logistic regression. Actually, give me 1 second here. Let me use the pointer. Okay, so that's better. So these are important concepts like what is machine learning, regression versus classification, logistic regression, so on and so forth, all these things. And then we're going to do a quick code walkthrough to walk you through the steps to implement logistic regression using Python. Okay, and then I'll answer any questions you guys may have. And then that's it. So that's the plan for today. All right, first of all, who am I? All right, my name is George. And in terms of talking myself, I'd like to talk about myself from these three bullet points. So number one, I am a lifelong learner. I learn really anything and everything. Okay, so what do I mean? So basically, for my undergraduate, I majored in mechanical engineering. That was like automotive engineering, but in China they they call it automotive engineering. So you learn a little bit of mechanical engineering and some maybe electronic stuff, things like that. So that was my undergraduate. And then for my master's, I did MBA at University of Toronto. So it's a business degree. Okay, and most recently, I also learned data science, programming, machine learning, all these things. So I really learned anything and everything. And yeah, I think that's my core competency, basically to learn stuff fast, okay, and apply it. So I used to be a management consultant. I used to be a management consultant. I think some of you guys may not have disabled your muted yourself. Can you please mute yourself so that everyone can be focused? Okay. So yeah, so I used to work as a management consultant, and right now I'm working as a data scientist with Chatter Research. It's a market research company, a market research startup here in Toronto, Canada. And by the way, Toronto is one of the major technology hubs in North America. And lastly, in terms of my specialties, as I specialize in machine learning, in specific, deep learning, NLP. And the other specialty area would be analytics. So basically, to pull data from database and build dashboards and so on and so forth, those things. So that is a basically, a quick overview of who I am. All right, and you have all my contact information across different social platforms. So feel free to connect with me, and we'll go from there. All right, so that's who I am. Now, I'd like to do a quick poll here to start off, okay? Because I want to understand what your knowledge level and comfort level with machine learning and also Python is, so that I can position myself, I can position, I can cater this this presentation to your specific needs. All right. So how do we do this? Let me go to the Zoom here, and let's see, or maybe I can do it here. Q&A notes. Okay, let's see. Actually, let's try Zoom. Sorry, give me 1 second here. I need to figure out where my chat box goes. I think I may need to stop the screen share for a second. Okay. All right, guys, sorry about that. Oh, someone says, Nikhil says no audio. Can you hear me? Can you still hear me now? I hope you can. So now, everyone, can you please in the chat box type yes if you are familiar with machine learning, or if you have some prior knowledge of machine learning. Okay. If you are not, then please type no. All right, just in here in the chat box. Okay, so yep, I got 3 yeses already. Thank you. Okay, heard of it, but not really. That's Plusha. And okay, so it seems like most of you guys have some prior knowledge of machine learning, so that is good. So Sassy says have basic knowledge on machine learning using R, but not with Python. Okay, understand. Familiar with the machine learning through Coursera, but not Python. Okay, I understand. Okay, so that is good. I think most of you guys have some sort of prior background in terms of machine learning. And then this user says just a beginner. Okay, basic knowledge of both machine learning and Python. Okay, that's good. And yeah, so how about Python? Do you guys have knowledge about Python? I know some of you have already mentioned that you learned R or a little bit of Python. Okay, so I got that. Basic knowledge, okay. Thank you. Familiar with Python, okay, beginner. All right, no knowledge of Python. That's Shubham, okay. I know R. I started learning this from March. All right. Yes, basic programming. Okay, I got you. So that's good enough. Thank you to everyone. Thank you guys for the information. So my understanding is most of you have some sort of understanding of machine learning, but when it comes to Python, probably you know, the comfort level varies. Okay, so also you know, I'll go into details and slow down whenever I need, whenever I see fit. Okay, so that's it. I'm going to go back to the screen share. Okay, and then we're going to continue with our presentation. All right, guys, you should be able to see my screen again now. All right, so let's go to the next slide. So yeah, regarding what you will learn today. All right, so these are the things you're going to take away from today's session. So first, a solid understanding of how logistic regression works. And second, you're going to have a strong intuition about how learning happens in machine learning. And you're going to learn one of the most important concepts in deep learning, which is a gradient descent. Someone is going to say, hang on, am I supposed to learn logistic regression or deep learning? Well, here's the thing. Deep learning, you know, if we treat deep learning as a you know, a big machine, then logistic regression is just the smallest part you can find in this machine. Okay, so once you understand how logistic regression works, you are going to have your first important step towards deep learning. So that's the idea. And the third point, the third most important thing you are going to learn is you are going to have a clear grasp of steps to implement logistic regression from scratch. And lastly, you're going to have the ability to build a logistic regression model using SKLearn right after this session. So those are the things you are going to learn today. So most of you guys have some sort of understanding of machine learning. So let me just quickly go over this anyways, okay? So first of all, what is machine learning? So machine learning my understanding is, of course, we can find many definitions online by a quick Google search. But I think if I'm to define machine learning, I think it's just a way for computers to do simple tasks such as classification without being specifically, explicitly programmed. For example, if we do image recognition, maybe the picture of a dog, then we can describe. If we are to write a computer program, then we are going to say, for example, what the dog looks like, maybe where the ears are, and how the dog's face looks like, and how the body looks like, those kind of things. You can do that, right? But the thing is, given the different kind of situations you are going to encounter, this kind of specific explicit programming will be very hard. Because imagine, what if the dog is instead of sitting in the sun, is sitting in a very dark lit room, right? Then it'll be very hard because your program will not be able to capture all the different scenarios and the different situations. And look, that's explicit programming. But then with machine learning, what you can do is you can write up an algorithm, and this algorithm is going to learn from all these different pictures of different scenarios, like the dog sitting in the sun, the dog sitting in in the shade, and so on and so forth. And then it's going to learn basically a process to identify all these different pictures to say, look, this is a dog. So that is machine learning in a nutshell, okay? And then in terms of machine learning, we can further divide machine learning into a couple of major categories, okay? So first we have supervised, and then we have unsupervised. So what is supervised learning and what is unsupervised machine learning? Simply put, whenever you have a label, whenever you have the ground truth, okay, then we say this is supervised machine learning, because the model is learning from existing data and the corresponding labels. So using our prior examples about dog pictures, then we can say, now we have a picture that's data, and on the other hand, we have a label saying this is dog. And then we have another picture saying, this is a cat picture, and then we have a label saying this is a cat. So whenever you have labels, okay, whenever you want to learn from that kind of data, then you're doing supervised machine learning. And then there is unsupervised machine learning, which is on the screen here. That would be the two parts at the bottom. So there is a clustering, there is a dimensionality reduction. So for those, you wouldn't have any labels to tell you what they are. So I'm not going to get into the details for these because that's not the focus for today. But regarding machine learning, we just talked about the supervised machine learning. Actually, both classification and regression, they belong to this category. They're both supervised machine learning. For classification, you basically give a binary label to a specific sample. Okay, say a picture, you say this is a dog or a cat. So that's classification. And then regression is basically to predict a numeric value. All right, for example, you're going to predict the temperature, today's temperature. So that is a specific numeric value you're predicting. It's not a class. Just now we said that this is dog versus cat, so that is a class. But here we're saying the temperature will be 23 degrees Celsius or something else. It's a continuous value you are predicting. So that is regression. All right. So that is the difference between regression and classification. And now we are going to talk about logistic regression. Okay. So we just said logistic regression is actually, we just said regression is to predict the value. Then how about the logistic regression? Well, the answer is logistic regression is really a classification algorithm. Okay, instead of predicting a numeric value, you are predicting a class here. So we can actually use logistic regression to make predictions about pictures, to say whether it is a dog picture or whether it's a cat picture. So logistic regression, even though it has the word regression in it, it's really a classification algorithm. Okay, and why do we have the regression word in it? Well, because it is a combination of linear regression and then a classification algorithm. That's why. So a logistic regression model, simply put, it is a classification algorithm that combines your linear regression, okay, with a sigmoid function. I'm going to talk about what a sigmoid function is in a second, but let's come back to the linear regression concept we talked just now. Okay, actually, I'm going to start using annotation on the screen now. Hopefully, you can see this. Let me go somewhere. Give me 1 second. All right, so. Okay, let me make this little. Okay, so that is good. So clear. Okay, so now if we're talking about linear regression, we have a bunch of points, right? We have all these points that we're drawing that we have as our data points, and then our job would be to find the best fit line, you know, that minimizes the error. Basically, the error would be the distance between all of these points to the line. So that's linear regression, right? But now from linear regression, which is really to predict a numeric value, to predicting a class. For example, in this case here, we want to say whether, you know, the sentiment is happy or it's sad. So these are different classes. So how can we go from a linear regression to a binary classification situation? So the answer is a linear regression doesn't really give you this binary kind of outcomes, right? So we need a function that can actually, you know, that can actually introduce non-linearity into the linear regression. So that is the sigmoid function. Okay, basically that's the what we see in here, and that's what we're going to talk about. But before we move on, okay, linear regression part would be on what we see on the left side. What does it mean? Remember, let me just change this a little bit again. Okay, so remember a linear regression from our statistics classes before. What it is basically you have a bunch of, so from a statistics standpoint, people usually use betas, right, as the parameters. So beta 0 would be the intercept, and beta 1 would be the, and this would be x1. Beta 1 would be the first coefficient, and beta 2 would be the second coefficient, and then the second variable. Okay, so that's kind of like the linear regression. Okay, and you see all these different variables, and then theta 1, theta 2, theta 3. So that would be the same as your beta 1, beta 2. But of course, there isn't a bias term here, which is intercept. But that's kind of the idea. Now, again, this is a formula for us to predict a continuous numeric value, but we don't need a continuous numeric value, right? For example, we can predict a 1.1, 2.3, and maybe 1,000, and any numbers really with this kind of linear regression function. Okay, but that's not going to help us. How are we going to jump from a linear function to a nonlinear binary function or binary prediction? So that's what we're going to talk about in the next slide. Okay, so let me clear this, and I'm going to close this, and let's come back here. So yeah, so that's what the sigmoid function is supposed to help us with. Okay, from linear to nonlinear. Specifically, not just a nonlinear. We want the binary outcomes. Okay, So either this or that, either white or black. Only 2 outcomes, not more than 2. So that is called, to help us achieve that, we need a function that's called sigmoid. What is a sigmoid function? Basically, this one you see here. Sorry, let me go back. So this is how the sigmoid function looks like, which is a 1 over 1 plus, this e represents the the base of a natural logarithm, which is you can just simply think of it as a 2.7 or something. Okay, that's a fixed constant number. Okay, 2.7, let's say. But in math, they just use e. E raised to the power of minus x. Okay, so you enter x value here, and then you calculate the y value, and then we can plot it on the on the coordinate system, and then we can see this. Okay, we can see this plot here. This is very interesting. Why? Because look, on the x-axis we have all the numbers from minus 10 to positive 10, and any real values in between. Right? For example, minus 9.5 or positive 5.61, all these different values. But then when you look at the y value, okay, it's basically limited and bounded between 0 and 1, right? So it doesn't go above this. So later on in the programming walkthrough, I'm going to show you guys that even if you extend this minus 10 to minus 1,000 or positive 1,000, this the value is not going to the y value is still going to be limited between 0 and 1. And this is a very important characteristic of the sigmoid function. Why? Because what we can do here is that we can treat the y value as probabilities. And we can say whenever the probability, so we have 0.5 here, whenever the probability is bigger than 0.5, we say this is class 1, right? Over here. We can say this is, we can say this is class 1. And whenever it is, the y value is below 0.5, we can say this is another class, for example, class 0. And you see, by doing this, we converted the numeric x value over here into a binary outcome. Basically, this one here and this one here, either class 0 or class 1. So that's what the the important thing that a sigmoid function can help us with. Basically, to help us to make binary predictions, even for numeric values. So that is your sigmoid function. All right, it is the basic the one of the important things, the most important things actually in logistic regression. Now, we talked about the sigmoid function and how it can help us to go from a linear equation to a nonlinear binary outcome prediction. Now let's go into the details to see how exactly logistic regression works. Okay. So first of all, over here you see a linear regression formula, as we just saw on the previous slide, right? Sorry, which says y is equal to b plus w1 times x1 plus w2 times x2. All right, so the b would be the intercept, w1 is the first coefficient, w2 is the second coefficient, all these things, right? So whenever if you have all these different parameters, b, w1, w2, and then you can make your predictions for what y is given x1, x2 value. So that is what a linear regression function is. And the second one is the sigmoid function we just talked about. Okay, so how do we combine the two to make binary predictions? Actually, we just need to substitute this part here linear regression function here over here into the x, right? So instead of using just any number, we're going to say we're going to use this, the linear combination in place of this x, which gives us this equation here, right? So now you have this equation saying y is equal to this 1 over 1 plus e to the minus, and then again, this thing is not an x anymore. This is the linear combination. So that's how you combine the two, into a logistic regression equation. So just a quick high-level understanding, just to give a quick high-level understanding of how this thing works. We have this equation here. That is good. And now we also have a data set at the bottom left corner here. Okay, let's imagine we have x1, x2, and y. So y would be the label we're trying to predict. So for example, for the first sample, we say x1 is 0.5, x2 is 0.6, and then the corresponding y value is this, and so on and so forth, right? So this is the data set. This is the data set. Now, we have this equation here in front of us. How can we leverage this data set so that we can actually learn a formula that can predict the corresponding y given x. So say, for example, if we have a new data point saying 0.3 here and 0.1, is it going to be the y value or the class label, is it going to be 0 or 1? How can we do that? It turns out what we need to do here is really we want to adjust all these parameter values, and then until at a certain point the prediction is accurate enough. Okay, we just adjust these b values. So what you see here is a question mark. Okay, so what is a ideal b value? What is the ideal w1 value? And how about w2 value? What are the ideal values so that this formula here, it can make most accurate predictions? So that is what we are going to ask this equation to learn. And that is really the machine learning, to learn all these parameters, okay? Just a quick definition here. So the difference between your actual y value, which is also called ground truth. So all these are true labels, okay? And then the y hat here means the prediction, right? So if the real value is 1 and you're predicting 0.9, that 0.9 would be your y hat value and the y would be 1. Then the difference between the two, the 0.1, that's going to be called the loss function. That's going to be called the loss, okay? And the function to calculate the loss would be a loss function. So this notation here, what it says is the loss function of your predictions. Basically, that's what it is. What is a loss? A loss is also called an error. Okay, so whenever you make a prediction, you measure how precise it is. That's the error, because you as long as your prediction is not 1, then there is always an error there, right? Even if it is 1, we can still say the error or the loss is 0. So that's what loss and error are. Okay, so and overall, this is how logistic regression works. All right, so that being said, let me go to the next slide. Okay, and we're going to talk about how to make predictions using logistic regression. Sorry, give me 1 second. All right, so now so on the previous slide, we talked about how logistic regression works, right? But how do we make predictions? Well, we just talked about our job in terms of building the linear regression, logistic regression model, is to find out what all these parameters are that can make the best predictions with which is the predictions with the least error. However, remember, all these predictions, they are still going to be numeric, right? Maybe 0.8, 0.3, all these things. Although they are bounded between 0 and 1, they're not the binary outcomes yet, right? And remember what we just said when we were talking about the sigmoid function here. We said if the y value is bigger than 0.1, we're going to say this is a class 1. And if it's otherwise, this is a class 0, something like that. So we can then implement this, exactly like what I just said. If the y hat value, if it's greater than or equal to 0.5, then we say the prediction is 1, class 1. Otherwise is class 0. Okay, so that's how you make predictions. So using the logistic regression equation over here, we do the calculation. We do the calculation to have our y hat, and this y hat we're going to plug it in here to say if it's greater than or equal to 0.5, it's going to be class 1. Otherwise, it's class 0. So that's how you make predictions using logistic regression. So next, let's talk about how machine learning really happens in logistic regression. Okay. So overall, I think we're going to talk about the loss function, cost function, and gradient descent. But overall, let me just give you guys a high-level understanding of what how the learning happens. So remember, just now we talked about a loss function. All right, and think about it. We have many different data points, not just the one, because for one data point we can calculate the loss, right? For example, this loss here, if we simply say the loss is the difference between the two, then the first one would be 0.8 minus 1, that would be minus 0.2, and the second one positive 0.2, and the third one would be minus 0.1. All these will be losses, but remember, we're not looking at one data point, one row, or one sample. We're looking at the whole data set, right? So our prediction algorithm, it should be able to make the predictions accurately enough that it's the error on every single sample is minimized. So it's not only for once, for all of these different samples. So in that case, okay, so we say for each sample that is a loss, but when we combine everything, when we add them together, okay, that's going to be called a cost. And then correspondingly, we can express how the cost changes using something that's called a cost function. Okay, so now back to this. So once we have the cost function, all right, our job is then to minimize this cost, right? So remember, the cost is the total losses for all the data points, and that's exactly what we want. We want to minimize the prediction error on every single sample, and hopefully it's going to work for every single sample in the future as well. That by saying all the future samples, I'm talking about the samples that our model is not trained on, or the model hasn't seen yet. Okay, so then the learning here is really to minimize the cost function, and the cost function can be in a multi-dimensional space. So instead of a one-dimensional or two-dimensional, it can be in a 3D space, right? For example, in this case here, we have two variables, okay, defining the cost function. the cost function is driven by these two variables. And now if we plot this cost function in this 3D space, we can see something maybe like this. So our job in terms of machine learning, okay, is then to find the x1 and x2 values that gives us the lowest point in this cost function here. Let's say it is this point here, okay? It is this point here. Then our corresponding x2 and x1 value would be these and these values. So our job, again, is to find the x1 and x2 values that minimize our cost function, all right? And how do we do that? Well, here, I have to clarify a little bit here. It is a little confusing that we're seeing x1 and x2, but these really, they are the parameters. For example, they can be w1 and w2, which are the weights, the w1, w2 here. So really, I shouldn't use that picture because it says x1, x2, because they are really w1, w2, right? Because our job, remember, is to adjust the w1, w2, and the b values so that this loss is minimized. And again, the cost of the whole data set is minimized, right? So that is kind of the idea. So again, the learning is to vary all these parameters of your logistic regression, which is the weight and the weights and the bias. We need to verify. We need to adjust all these, right, until we find the minimum point in this cost function, and that concludes our learning, machine learning. Okay, so that is what it is. So this whole process of finding the minimum point of this cost function is called the gradient descent. We normally use gradient descent algorithm to find a function like this minimum point. Okay, so that is for this slide. So next, let's talk about how we do this training in details. Again, we're looking at this data set here, right? So you have your x1 value, x2 value, you have your actual y value, and then you also have your y hat values. Again, these are the predictions you made based on your equation, okay? And what if your equation is not there? Someone is going to ask me, the whole point of doing this is to find out the mapping equation, right? The formula to calculate the y hat. How would I be able to calculate the y hat? Well, we need to start from somewhere. We can just simply initialize all these parameters like b, w1, w2, all these values with some random numbers, or maybe just a 0, okay? If we do it that way, then we're going to get, in this case here, number 0 in here, right? So minus 0 will be 0, e to the 0 will be number 1, and then we would have a y hat of 0.5, even if we initialize all these numbers as 0. So you see, we can start from there. So if we do that, then we're going to have our y values. And then for each of these samples, we can find the loss, right? So for now, let's just think about the loss function as simply the difference between the actual y value and the predicted y value, just the difference. But later on, I'm going to explain or define a different loss function. Again, for each sample, the error in the predicted value would be called loss. So we have a loss for each of these predictions. Okay, so all of these different losses, and again, the cost here would be defined as the total of all the losses. So you have a loss for this sample, you have the loss for this sample, and this and this and this, all these. We're going to add all them up, okay, using this sigma sign here. In mathematics, it means basically to add everything up from, from I equals 1 to m. Basically, the I, you see the I here, that's the superscript. So basically, when I is 1, we have a y1 and y hat 1, right? So we have the loss. And then you have, when I is equal to 2, you have y2, y hat 2. You have that loss as well. And then you add all those together. So that's exactly what we said here, add all the losses together. And then you have this, this cost function. So the cost function is really for the whole data set. You add all the losses together and you have the cost. And then we call that J, okay? So we, on the previous slide, we said our job in machine learning is really to minimize the cost, okay? How do we do that? Well, because the cost is made up of all the individual losses. We add them together, we add them up together, okay? And then for the y hat or the predicted y value, we can use this, we can use, actually, I think I made a mistake here. This function, I forgot to put in the sigmoid in here. So it should look like this, okay, this one here, and not that. So I used this as a mistake. It should be this one. Okay, sorry about that. So our job, again, is to adjust all these parameters so that the individual losses, they are minimalized. Most importantly, is the total cost that's minimalized. So that is how we do the optimization. We need to do optimization to learn all these parameters, and that'll give us the the best solution to make the predictions. So now here we're going to talk about how gradient descent happens. Okay, so this is a very important concept. It's going to be, it's actually called one of the most important concepts in deep learning. So it's important that we understand this well. Okay, so just now we said that machine learning here is really to find the best combination of our parameters, including the bias and the weight values. We need to find that best combination that minimizes our cost function J here, right? So if we are to simplify this a little bit, instead of saying that the cost function is in a three-dimensional space, we're going to say we only have one parameter that we need to optimize. Let's say this is W, which represents weight. Okay. If we only have that one parameter to optimize, if our cost function looks like this, okay, then the question becomes, how can we vary our W value so that we can find this most optimal point on the cost function here, right? How can we find this point here? Because this point gives us the lowest, cost function value in this function here, right? So our job is then to find this W value. How can we do that? It turns out that there is a very great concept in mathematics and machine learning that's called the gradient descent that can help us achieve this. Okay, because now let's say you are, like this is a big curve, and then we're just walking on this big curve, and then we're walking from here, and then we're going to ask ourselves, where do we go so that we can get to the bottom? Well, I mean, in real life, if we're standing there, we will be able to know where to go because we can take a look and we can say, well, look, I can go down the slope here, right, to the bottom. But remember, we're not, the point A is not a human being, and it wouldn't be able to do that, to look at the bottom, where the bottom is. So how do we do that? Well, it turns out what you need to do is only to calculate the slope here at this point A, and then you can use the slope to guide you, right? So if the slope is negative, you are going to increase your W value, which means you go towards this direct, you go towards the right, right? So that is a very important insight here. So you calculate the slope, and then depending on whether the slope is positive or negative, you go towards the left or the right. Let's see whether that's correct as well when we are on this side. So if we are here, the slope here would be like this. So that is a positive slope. So for a positive slope, we need to go towards this direction, because just now we said when the slope is negative, we go towards the right. Then when the slope is positive, we go towards the left, right? So that's exactly right as well. So let's say now you are standing here. For this point here, the slope would be positive too, right? So then again, you are still going towards this direction until you reach the bottom point here. So look, is how beautiful that is. By simply calculating the slope, you can find the direction you are going, as if the little point there, it knows, like us as human beings, we can take a look and see the bottom is there, and I can go towards that direction. So that has exactly the same capability, which is really nice. So what I just explained, that's basically in a nutshell what gradient descent is. Okay, so what is a gradient? Well, a gradient is just a slope. Okay, gradient is just a slope. And there is another word that people often use as well, is derivative. I think these three words, they are more or less interchangeable. So when people saying there is a gradient, there is a slope, there is a derivative, they're more or less the same thing. So in terms of mathematics, basically, whenever we calculate the slope, that is going to be the tangent of a curve at a certain point. And to calculate the tangent, that's really to find the derivative of this function at this point. Okay, and how can we do that? So a quick walkthrough. Let's zoom in a little bit. Okay, for this point here, we're going to make this larger, and let's take a quick look. So we are now standing at this point. Okay, and remember, we were saying if we are to move to the bottom, which is here, right? Which direction do we want to go? Now we say if we nudge our value, our W value a little bit, okay, a tiny little bit over here to the right, then how much our J value, the cost, will change. Okay, so that's going to be the derivative. That's going to be the derivative, which is defined as a infinitesimal, a very, very small, okay, change, small to a certain point that is so small that we can't even draw, but as small as you can go. So when you nudge the W value a very small amount, how much does your Y value changes? And you can express that as a fraction, right? So this change divided by that change, or the cost change as a result of the weight change. So if you write it out, it's going to be something like this. But notice that I have a delta here, the triangle. But here, how come I have D? Because that's essentially the same thing. As we just said, derivatives, they are just your slopes. They are just your gradients, right? So here we're saying this little change is going to result in this little change in your cost. And then we're going to express this in derivatives. So that's a derivatives definition in mathematics. That's exactly the little slope here. Basically, this value divided by this value when they are both, very, very small. Okay, so that is what it is here. So what you see here would be derivative of j, the cost function, with respect to the w variable. Okay, so this in total, dj divided by dw, that's the derivative at this point. Okay, that's also the slope, or also the gradient. And now the actual function, the actual equation to do the calculation to update the w value will be like this. Okay, so once we calculate this, we're going to say the original w value minus alpha, which is the learning rate. I'll talk about that in a second. Minus the learning rate times this little derivative thing. Okay, so in this case here, if we're going towards the right, which is to the bottom, right? So a little change in w, this would be positive because we're increasing the w value here to the right, but the j value is going down. So that change is going to be negative, right? So this here, dj divided by dw, so minus divided positive, that's going to be a minus value. And then there is a minus sign here. So then we're going to see w plus something, which means we're going to increase the w value. Is that correct? That is correct, because we want to go towards here, and we have to increase our w value to go towards the bottom. And that's exactly right, right? If we're to test this again on the right-hand side, then we can look at the B, the B point here. Again, we're going to zoom in, and we're going to look at this. So at this point here, okay, if we are to change the w value a little bit, let's say we're going to increase this a little bit. How much does the j value change? Well, this j value will go up as well. So both are positive. Then this value here will be positive too. So then we are decreasing the w value, meaning we're going towards the left. So again, that is correct too, right? From here, we just need to go towards the left to find the bottom point. And you see, this is really very powerful, because this gives exactly the capability of finding the bottom point, or which direction to go towards in finding the minimal point in the cost function. Initially we said, as human beings, we can take a look and see where to go. But for these mathematical formulas to work, they wouldn't be able. They don't have eyes. They can only do these calculations. So that is the eyes of the machine learning algorithm to see where you want to go, which direction to go towards the bottom point or the minimal point in the cost function. Okay. Again, when this thing here, when it's positive, right, we're going to go towards this direction, okay, which is to reduce the w value. When this thing is minus, we're going to go towards, we're going to increase w value. So that's the idea. And the learning rate alpha, what it is basically, as the name indicates, is how much you learn each time, how fast you learn, right? So because we're going to update the weight value, right, with this times this. So if this alpha value, the learning rate, is very big, then every time we're going to update the weight value by a lot, okay? And sometimes it may not be a good thing, because if you are standing here and then you're updating a lot, then maybe you go too much, you go here. And then next time, if you update a lot, then you go here, then that's going to be a lot of noise and a lot of runaround that doesn't happen, meaning that your learning will take longer, right? What if you update a little less? Then you can simply go like this, okay? And then you go very quickly to here instead of like running like this. It takes forever for you to arrive at the bottom. So that's what the alpha or learning rate does. It controls how fast you learn. Okay, so that's how gradient descent works in a nutshell. Sorry. So now we understand this from a conceptual standpoint, but in terms of implementing this, in terms of using our code to express this, we still need to figure out how to calculate this quantity here, right? So that's why we need to jump into the details for this as well. But you know what? It looks complicated. It is not as well. It is not at all. And I'm not going to go into the mathematical details at all because it's not needed. Trust me, guys. What you need to know is only conceptually how this thing works, and then you just need to know the final formula. That's it. Then you will be able to implement this using code. That's all you need. But for the sake of completeness, let me just quickly go over this. So we said we have a cost function, and we want to find the derivative of the cost function with respect to the W or the weight variable. So now this thing here, right, the cost with respect to the W, the weight, that's something in calculus there is a concept that's called the chain rule. What it means is that whenever you have something you want to calculate, you can if this function can be expressed in different other functions, then we can multiply all these individual derivatives together to get the overall derivative of this thing. What does that mean? Because this cost function with respect to W, this derivative is hard to calculate, but we can decompose this a little bit. So dj divided by dw1, right? So what is the j function? So the j function, the cost function, remember, it's the summation of all the individual losses of different samples, right? For example, you have m samples in your data set, then it's a sum of all these m samples. All right, so we can express this cost function like this. And again, your y hat or your prediction, it can be expressed like this, which is the sigmoid function, right? So 1 divided by 1 plus e to the z. So that's how you can express this y hat. And then your z, remember we said we just plug the linear regression equation in here. So the z can be expressed with this linear regression formula as well. So you see, j can be expressed by y hat, and y hat can be expressed by z, and z can be expressed by w1, right? So now we established the link between j and w1, which is, now because we want to find the derivative of this function with respect to this thing. So now with the chain rule, what we need to do is just to find the derivative of these three functions individually, and then we can just time them together simply as that. So dj divided by dw1 would be dj dy hat, which is the derivative of this function here, right? And then the second one would be the derivative of this function here, and the third one would be this derivative of this function here. And then we time them together. And one thing to note would be, because we are taking the this thing here is basically, I think I kind of made a mistake here. I shouldn't use the m1 over m here. There shouldn't be this. Okay, it should be an individual loss. So it turns out in order to calculate the derivatives for all the different losses, we need to take an average as well. So that's why we have this term here. Okay, so now our task is to find the individual derivatives and then time them together. It turns out this first term, the derivative would be this thing here. And for the second one, it's this. For the third one, it's this. Then we can do the calculation, and then we get this. Okay. Later on, I'm going to show you. You don't have to know the calculus to do the calculation to find the derivatives at all. Okay. You can do this online using a tool. I'm going to show you. But what this says is that the cost function, the derivative of the cost function with respect to the W1 variable is equal to y hat minus y times x1 times 1 over m. So the x1 here corresponds to the W1, right? Because we're saying to calculate the derivative of this thing, we need to use, also here we need to say y1 hat and y1 as well. Again, I missed those things, so y1 hat. So we need to use all those values for the first sample. And then, oh, sorry, I mixed this up. For the y, so the x1 here would mean the x1 should be the superscript here. It means the first sample, not the first variable. Sorry about that. Yeah, but this is the equation you need to use, okay, to calculate the derivatives. So now we need to implement this in code. How do we do this? So these are the steps. I'm going to talk about those in details later on when I do the code walkthrough. Now we are going to do the code walkthrough. Okay, guys, hope you're ready. So let me get my my code ready. Give me 1 second here. Okay. Sorry. Okay, all right. Now, guys, can you see my my screen? Yeah. So I have my Jupyter notebook here ready. Can someone maybe just sound off if you can see my screen? Just want to confirm, please. If you can just say yes. All right, I think you should be able to see. All right, so yeah, so this is the notebook. Let's do the walkthrough. Okay, so first we're going to import all the necessary libraries here that we need. Okay, so those libraries, and then we talked about this sigmoid function. That's how it looks. Okay, it's the same thing here. And in terms of code, we can implement it this way. So the sigmoid function, you have an x value, and then the y value can be calculated as 1 over 1 plus, and then e to the minus x. And so NP is numpy, right? So we're using the numpy exponent function here to calculate this e to the minus x, and then return y. So that's our sigmoid function. And then we can also plot this, right? If we plot this, we see that's exactly how we describe this, right? So between -5 and +5, we have all the values bounded between 0 and 1, right? So that's good. And then how about -10 and +10? right? Well, you see, it's still the same thing. The y value, it doesn't go over 1 or below 0, right? So how about minus 1,000 and positive 1,000? Well, you see, it's still the same thing, right? So you see the y value, it doesn't go above 1 and below 0. And that is a very important quality here, because as we said, we want to convert a numeric value into a binary value. And that's exactly what we wanted, right? This is the probability, and then whenever your value is above is greater than 0.5, we say this is class 1, otherwise it's class 2. So that's perfect, right? That's why we use the sigmoid function. And then we talk about the loss function, right? So just now, remember, I was talking about the loss function simply as the difference between our prediction, the predicted y value, and the actual y value. But it turns out in real life, we actually use a different loss function, which gives us a better, better handle of things in terms of calculating the gradient descent. So what is the loss function then? It is this thing here. Again, I'm going to let me just use my highlighter here somehow. Okay, so annotate. All right, so okay, so look, so basically this is the loss function. That's how I calculate the loss. Okay, so y times log y hat plus 1 minus y times log 1 minus y hat. So that's the loss function for each combination of y and y hat values. We can calculate the actual loss. Again, that's for individual samples. And now for the cost function. For the cost function, we said this is really the total of all the losses. So you see, we use this sigma sign here to sum up all the individual losses. So that's that part. And for the gradient descent, remember, sorry, we were talking about how to calculate the derivative of this cost function with regard to the to W1, and then we talk about how we can use the chain rule to break down this thing into 3 parts. So the first part will be this equation 1, second one will be this, the third one will be this, and then really the cost function here. Actually, I think I made another mistake here. It should be the I think it should be the J. The letter should be J instead of L, which means we want the derivative of the cost function with respect to the. So here I used the bias B here. Really is the these 3 parts. We time them together. And again, how we are going to calculate this? We just need to find the individual quantities. We time them together. And just now, I promised you to show you how to do the calculations. So, for example, how do we calculate this? The loss function, the derivative of the loss function with respect to the y hat value. Well, we can use a tool that's called Wolfram Alpha. So in here, if you enter your expression like this, it's going to give you the derivative. Okay, so you don't have to know. It's going to give you this, all right, which you can prove is exactly the same like this. But here, the h here is just the y hat. Okay, y hat minus y divided by y hat minus y hat squared. So that's how you can calculate for all these 3 parts individually, and then you just time them together. You have this, right? So that's that. And then similarly for the so what we did was for the bias. Now how about the weight? We can do this same thing, right? And then we can calculate like this, right? So and finally the formula. you know, the those are for individual losses. And if we're going to calculate this for the total loss function, oh, so then you know what? Then I didn't make a mistake here. Actually, these are indeed for individual losses, so those are good. So for the total cost function, we just need to take the average of individual losses. So now, in order to implement this, right? There are a couple of things we need to do to implement the logistic regression algorithm. So first, we need to have a data set. So I made a data set here. I'm not going to go into the details for this one here. It's pretty straightforward. You can go over these later on your own. And we split the train test set so that we can test our model. So in order to implement a logistic regression, right, we can reverse engineer. Think about the end goal, what the end goal is, and then we can think backwards to see what we need, right? And that's how I come up with these steps. So at the end of the day, what we are trying to do is we are trying to update our parameters, which are the weights and the bias, all these terms. So we want to update those. And in order to update those, we need to find, remember the you know, the formula we're going to use. For example, for W, that's W equals W minus alpha times the derivative with regard to W, right? So now we need to find that the derivative. So how can we find the derivative? Well, that's the derivative of the cost function with regard to the weight, right? But then we need to find the individual loss derivatives. Okay, so how do we find the individual loss derivatives? We need to find the individual losses, right? So then the problem becomes, first we need to be able to calculate the individual losses. Then we calculate the you know, we basically we first need to initialize the bias and weights so that we have something that we can start with, and then we can use that equation to make predictions. And once we have the predictions, we can calculate the losses using the formula we defined above here. This #1 equation to calculate the loss for each individual sample, right? So once we have the losses for each individual sample, we can calculate the derivative for those loss functions, and then we can take the average of those derivatives to arrive at the cost function derivatives. And finally, once we have that, we can update our bias and weights. So those would be the steps. Okay, so now let's quickly go over the code. So I used, I mean, if you're not very familiar with Python, let me just quickly talk about, you know, what the class here is. So class, basically, this is a way to do objective or object-oriented programming. Okay, basically, it gives you a very convenient way to associate your different functions and to define real-world entities. So that's what this is really about. So I'm going to define like a logistic regression model class, and under this class, I have different functions, which are really called methods. Okay, in object-oriented programming speak. So first, I need to be able to initialize my logistic regression model. Okay, and second, I need to train the model. So that's the train method here. And next, I need to be able to predict, to make a prediction using this this model. And finally, I should be able to test the model using the test method. So these are the 4 major methods that we have here. And next, so in terms of the first method, that's to initialize this class. Actually, to initialize the class, how what are the things we need to initialize? Well, first we have our training data, right? The X would be all the features, the Y would be the labels. So we need to have those, and we also need to be able to know, what is the number of rows in this data set and the number of columns. Why do we need to know that? Well, because we need to define the structure of our bias and weights, because the weights here is going to be a vector, okay? And remember, we said that we're going to initialize our weights as zeros. But even if we want to initialize as zeros, we still need to know the shape of this vector, right? Like how long is this thing, right? Basically, however many x1 we have, we need to have that many weights, right? So that's why I need to get the number of features, right? The number of features in here, and I'm going to initialize the weights using this. And for the bias, that's simple. I just need a 0 because there is only one bias. So now that we initialized our values, okay, next we need to be able to train. And for the train steps, it's just a matter of implementing all these different steps, right? So we've already done step number 1, and for step number 2, we're going to make predictions. How do we do that? Well, if we start from here, we're going to see, now we're going to do 2 for loops here, okay? The first for loop, we're going to loop through all the different epochs. What is the epoch? So whatever you learn from your data, you learn one sample by sample, right? Once you go through the whole data set, that's called one epoch. And normally in machine learning, you need to re-leverage the data, the whole data set again and again. So you do multiple epochs. That's why we do the first loop here. And for the second loop, we're basically going through every single sample, every single row in this data set to learn, okay? So we're saying for each row in this data set, okay? So we're going to define the X values. We're going to say for the input X matrix, we're going to get this current row. Let's say we're at row number 1. Okay, so that's row number 1. We have all the X values. And remember, this is not just a one value. This is a bunch of values like X1, X2, X3, all these things. So it's going to be a row vector. So we have that, and next we can also get the true Y values. Okay, and to make the predictions, recall we can use the combination of the linear regression formula and the sigmoid function. So that's what these two parts are about. Okay, so we have all the weights that we initialized. Then we multiply that with our X values. We get the plus the bias. We get the linear combination, and then using the sigmoid function we defined above, we can get the Y prediction. Okay, and quick note here: the dot thing here is basically dot product calculation in mathematics. You can search it up. It's basically how you can multiply two vectors or two matrices. All right. Now we have the Y prediction. Okay, we can plug in the loss function we defined above. Remember, it's equation number 1. We have the true Y value and the predicted Y value. We can substitute all those things in. We can calculate the loss for this sample. But then remember, we are most concerned about the cost. So we are going to accumulate this cost later on so that we can have an idea of what the cost is, so that we can print them later on. Okay. But then for the derivatives we calculated above, for the bias, it's really this Y pred minus Y true as we calculated above. And for the weights, whether it's weight 1 or weight 2, it's always Y pred minus Y true times X. So we calculate these things. And we also said in order to get the derivatives with regard to the the cost function derivatives, we need to get the average, right? We need to get the average. So basically, we need to add them together. Okay, we need to add them together here, and then we need to get the average by dividing the total number of rows. And now we have the derivatives. Okay, lastly, it's just a matter of updating them using the equation, the formula we defined previously. So that's how you do the tree method. In terms of the predict method, it's exactly what we said before as well. You just use this to do the prediction, and then if it's greater than 0.5, you're going to say this is 1. If otherwise, you're going to say this is class 0, and then you return the prediction. And there's a bunch of things here in terms of test. We're going to skip that for now. So that's how you implement this logistic regression from scratch. So I have another version here down below, which I used the vectorized operation, which is more efficient, because here, look, I use the 2 for loops. And for those of you who are familiar with the computer science, this is not the most efficient way to go about doing things. Instead, you want to vectorize things. So that's why, in here, as you can see, I get rid of 1 for loop, right? Instead of doing that, I used the vectorized operations in NumPy. All right. So now let's run this. Okay, we're going to run this, and then we're going to train the model. So how do we train the model? We're going to use this. We're first going to initialize or instantiate the model class we defined, and then we're going to use the train method to train, saying the number of epochs is 20. So let's do that. All right. So it does the training, and as you can see, for epoch 0, the cost is this, and the cost goes down, as you go through all the training epochs. So that is for 20 epochs. All right. So this is how the cost looks like. It goes down very quickly as we do the training, right? And again, remember, training here, the goal is really to minimize the cost, and we are achieving that because the cost goes down, consistently. That is good. Just now we trained for 20 epochs. Now we're going to train for 10 epochs. Okay, let's see how that works. Well, you see, it does pretty well as well. So probably we don't even need 10 epochs. So maybe how about 3, right? 3 is good too, because it goes down to this scale, less than 0.1, the cost, right? So that is very good. So now we're going to use the test method to test our model. And as you can see, the accuracy is 100%. Wow, that's good, right? So basically, the model is able to make predictions 100% accurately. How do we do this with SKLearn, scikit-learn, the machine learning library? It turns out it's super simple. It's even simpler than what we did above. So in real life, probably you're not going to implement your algorithm on your own every single time, because we have much more optimized versions done by other people already. So in this case here, we're going to use SKLearn. What you need to do is just to use this logistic regression class that they define, and then you want to initialize it and fit it on the train data set, and then you're going to make the test the model like this. Okay, so that's it, guys. So basically, that's the walkthrough of the code. We're going to come back to the slides, okay, and let's continue from there. Sorry, give me 1 second here. I'm just pulling up my slides here. All right, so you should be able to see my slide deck now. Okay, so we've just finished the coding walkthrough, so that is done. So the next thing would be Q&A. All right, everyone, it's the time for your questions. So maybe you have already typed your questions in the chat box. If that's the case, I'm going to take a look now. All right. Let me see. Where's my chat in here? Okay. Can we have distributor notebook, please? Yes, you. I believe you know the host, like GreyAtom, they're going to share with you. It's up to them. Okay. Okay. So yes. So let me make Canon the host. Okay. Give me 1 second here. Okay, I can see Swetha's question there. What is the cost function used in SKLearn? I believe it is the same as we did, although I haven't checked. I believe that's the same, which is the log loss. So let me make Canon the host. Let me see how I can do that. I'm going to stop my share for a moment and then make host. Okay, I've made Canon the host. So yeah. So let me start answering all these questions. Okay, so I'm going to scroll up a little bit. Let's see. Will the loss function always be negative? Well, that's the loss function. To be honest, I'm not sure what the actual values are, but you can do the calculations. But in terms of what the function looks like, yes, you have the minus sign there. That's how people define that. Okay, so yes. What is the cost function used in SKLearn library? Again, I believe it's the same, but I haven't checked. So the next question by Swati, we have to always compare the prediction value to 0.5. Yes, yes, that's how I do it. Yes. Other questions, guys? I think we have a couple more minutes because we were kind of late because of the technical difficulty. So now we have a couple more minutes to answer the questions, and then I'm going to you know, to give a closing remark. Any other questions out there? If no, I'm going to count to 10. If none, I'm going to proceed with the rest of the slides. Okay. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right. Seems like you don't have any questions. That is good. Okay. So let me close this, and again, I'm going to share my screen. Ooh. Hey, can you enable me as the host again? Because I need to share my screen. Hello? Hey, Kenan, are you still there? Can you please do me a favor by making me the host? Because I need to share my screen. Well, seems like Kenan is not responding. In that case, I'll just proceed. We just have one more slide left there, so you know, it's fine that you don't see the slides. Let me just talk about this. So yeah, we're going to. So that's pretty much it for today's session. Let me just quickly recap in terms of your key takeaways. So first of all, please remember, machine learning is just minimizing errors. Okay, as simple as that. So whenever we say machine learning, whenever we learn the machine learning process, it's just to minimize an error. It's just to minimize a bunch of errors, and in total, that's the cost, right? We want to minimize the cost of your. We want to minimize the cost of function. So that's the first thing. The second thing would be, remember sigmoid function, right? So sigmoid function, it helps you make linear non-linear. What does that mean? Basically, with your linear function, you're only able to make predictions for continuous linear values. But for us to be able to make binary predictions, that is non-linear, we need to use the sigmoid function. So sigmoid makes linear non-linear. Okay, and then the sigmoid function, it's important that you remember what it looks like. It's 1 over 1 minus e to the minus x. So that's the sigmoid function. And then the other thing to remember is that the loss is for one training sample, but you have all these different training samples. The total will be the cost. Okay, so that's the difference between your loss and your cost. And also remember, gradient descent. That's the one of the most important concepts in deep learning, in logistic regression. It allows you to find the direction for you to minimize your cost, right? Because our machine learning is really about okay, so I think I can. Sorry, I'm still not able to share my screen. That's okay. So yeah, because the machine learning is about minimizing the cost, right? So we need to be able to find the direction for us to minimize the cost, and gradient descent allows us to do that exactly. The next thing to remember would be the update equation, which is W equals W minus alpha times dj divided by dw for W, and for bias is bias equals W minus alpha times dj divided by db. Okay, and then the last thing to remember is use 0.5 as your cutoff value for making predictions. Okay, if your calculated y hat is greater than or equal to 0.5, we say it's class 1, otherwise it's class 0. And guys, and that's pretty much it. Okay, that's the major takeaways. If you are to remember a couple of things, please remember those things from today's session. All right, so that concludes the session. And just the 2 more things. So first, I want to congratulate you. Why? Because you have just taken the first step in your deep learning journey. Because logistic regression is really the most basic unit of your deep learning neural network. Okay, so you have just taken the first step. You have a solid understanding of logistic regression, and also very importantly, you now have a clear understanding of gradient descent, which is one of the most important things in deep learning as well. So that's why I want to say congratulations. And lastly, I wish you guys all the best in your future endeavors in machine learning and deep learning. Okay, all the best. So that's it for today. Thank you so much for taking your time to join me today, and hope our path can cross in the future. Thanks.
Log on to GreyAtom's learning platform to unlock more free content. Subscribe to our channel and hit the bell icon for regular updates.